Okay, so that's what we ended up the other day. We talked about the unit of the reaction rate, and I'm going to just continue on that one. Okay, so we cannot always state an overall. We cannot always state an overall reaction rate What does it mean? So if you remember, for those reactions that follow the polynomial or follow the power law, so you can add the order on each concentration or each reactant and say that's the overall one. But what happens if your reaction rate shows to be like with the numerator and denominator? So that will happen most of the time when you have gas-solid reaction. So is K N2O, concentration of N2O, 1 plus K prime concentration of O2. So if you look at it, we have numerator and denominator. This sort of form of the reaction rate happens when you have the gas-solid reaction. It's not like a simple power law one. Okay. So for this one, what is the overall order? So we cannot define any overall order for this ones, right? So the order comes on the reactant, limiting reactants. So now I'd like just to turn your attention to a very important Arrhenius equation. So Arrhenius equation what it does is shows you the dependency of the reaction constant on the temperature. So as I mentioned the other day, so there is a very strong relationship between temperature and reaction constant. So that's Arrhenius equation is the name of a scientist. Shows how this how this dependency takes place. So, like this is an important parameter, and definitely you might get the questions not for this quiz because this is a chapter 3, but later on. So just to make sure that you understand the relationship for reaction constant and temperature. So what do you think would be the relationship between temperature and reaction constant? So this one is, if you look at it, would be like minus RA, a typical power law reaction. Let's say is an N order. So we are talking about this. So if the temperature increases, what will happen to the K? So you expect K to increase or decrease? Increase, right? So it makes sense. Your molecule starts to move faster, and then so the reaction, the possibility of having the reactions and the impact of the molecules at a certain angle increases. Therefore, you expect to have more or higher rate of reactions. So as you guess, so is something like that. So that would be the reaction. So mathematically, the equation is defined like this. So we say K is A E minus E RT. This is the Arrhenius equation. So some book write K naught rather than A, but whatever notation different book uses, your book uses A. This is a pre-exponential factor. This A is pre-exponential factor. E is the activation energy. Okay? And what is R? universal gas constant, so PV equal nRT, so is a constant value. So you have to make sure, I mean, the only mistake that students make using this equation is just the unit, so the right unit, so just get back to 201. So obviously, what would be the unit of A? The same as A, right? So this one shouldn't have, but this package shouldn't have a unit. So in other words, E has the unit of RT, which is energy, activation energy, and A has the unit of K, and K has the unit what? Again, if you get back to last lecture, like K, you see the unit of K depends on the order of the reaction. We don't have a constant unit for the K, so it changes. Correct? Okay, so I'm going to write it down. What are each factor? Okay, so E is activation energy. E is activation energy. So is calorie per mole. Okay. R is gas constant or universal gas constant. Gas constant. And the unit was what? Calorie, mole, temperature, Kelvin, which is if you look at the number, that would be 1.987 calorie per mole Kelvin, or 8.314 joule per mole Kelvin. Okay, so T is obviously a temperature, and if you use this temperature set in other ones, so it would be in Kelvin, and A is a pre-exponential factor, is a pre-exponential factor, and or frequency factor, or frequency factor, right? And it has the unit of obviously K. So if you look at that equation again, I will write it down here. Again, if we write this equation, E minus ERT, what will happen if your temperature goes to infinite? I mean, very high temperature. So what will happen to your K? If this goes to infinite, so what would be? So basically this would be 0, e to 0 is 1, K approaches what? A. So and what will happen if you have very low temperature, like minus 273 degree C? No. If this goes to 0, so imagine this is a negative, so you have to, it's going to come to your denominator, right? And you're going to have a big number in denominator. So your K approaches 0, which should make sense, right? Because in minus 273 degrees C, you don't expect any reaction to take place, right? And that's kind of showing the motivation for reactants to make the reaction happen. And then on the other hand, A is kind of like from physical point of view, shows the when the temperature goes high, your gas constant, your reaction constant approaches A. So A shows you what would be the maximum value that K can have in extreme temperature. Correct? That's kind of a physical meaning of K. Okay, so again, just to put some definition on the board for simple reactions, in which two molecules collide. Let's assume we have two molecules collide. The pre-exponential term, can be thought as the frequency of collision of molecules, as the frequency collisions of molecules. Okay, I will write it down again here. The pre-exponential factor can be estimated for gas phase reaction, from the collision theory, based on kinetic theory of gases. Okay, what I have written here says for simple reaction in which two molecules collide, the pre-exponential term can be thought as the frequency of collision of the molecules. Just shows how frequent molecules are hitting to each other, right? You remember, again, for those who just did the undergrad, the first year here, so course 201. So in the chapter that we talked about the gas molecules, we went in depth how does it work and how do you calculate these collisions. Okay, so that's kind of, you can think about it. So A is going to be representative of the frequency of the molecules to hit each other. And obviously the higher this number is, means that there is a more probability of having the molecules hit each other in the right angle, right positions, and so you have more chance to get the more product. The pre-exponential factor can be estimated for gas phase reaction from the collision theory. If you remember kinetic theory of the gases, again in 201. So we don't get to the detail of that one, just to show you what is behind this term. So then when we talk about this one, so you don't think, oh, what is this, what is that? So basically shows how the molecules can collide and what would be the possibility of having the reaction to take place. Correct? Yes, please.
In the equation, what value for temperature would you use, since wouldn't the temperature change as we proceed with the reaction?
Yeah, so basically, a very good question. The question is what temperature you use for that Arrhenius equation. The temperature is the temperature of the reaction. So most of the time we are dealing with the isothermal values. Isothermal reactions means that you have dealing with a certain temperature. Is it room temperature? Is it 60 degrees C? Is it 100 degrees C? Whatever. But at some occasions that you might not face that much in that course, you are going to deal with the adiabatic condition. That means that your system is very isolated. So if the system is isolated, it doesn't allow the heat go on or in. So what will happen, either your temperature is going to drop if it's an endothermic reaction, or if your temperature start to increase if it's an exothermic reaction. So therefore, you have a range of the temperature. For that one, you cannot plug one single number to the equation. So you are going to have a range of the temperature. Obviously, you're going to have a range of the reaction constant, right? But for when you are dealing with the isothermal condition, you are going to plug in only one temperature, which is the reaction temperature. So just again get back to that equation that I put it there. Would be K is A E minus ERT. So like we are going to just do some examples during the tutorial. You will see that if you have the T, if you have the way that you calculate the parameter, which is A and E, this is called kinetic parameters. This is called kinetic parameters. So one thing that we do even in our research, we like just to find out what is the kinetic parameters for the certain reaction at certain temperature or so. So how do you calculate this A and E? Look at this temperature, look at this equation. So if I take ln from both sides, would be ln K, would be ln A minus ERT, correct? Correct? So if I plot K versus 1 over T, right? If I plot this versus this, and if you do that one in a semi-log graph, here is log and here is the normal, or you take the ln of this number and plot it here. So what you expect? How you gonna find E over R, and how you gonna find A? Yes, very good. So it's gonna be this is a equation of a line, y equal y naught plus mx, right? Right. So basically that would be a line, and the negative sign shows that you have a slope, a decreasing slope. So the slope would be minus E over R. Obviously the slope is negative, this negative cancels out, and you have the value of R. Easily you can find E from here, and then the intercept would be ln A. So basically where it hits here, so this value and the value, the slope, that gives you the ln E and A, you can calculate it. Yes, please.
Shouldn't the y-axis be ln K?
Well, I mean, what I wrote here, if it's depending on if you use the semi-log or if you don't use it. If you use the semi-log one, you just plug it in. But if you use just a regular graph, so you are right. So it would be ln K. But if you there are some graphs that gives you here is the logarithmic value. So then you plug the K as it is. It depends. I mean, it doesn't matter what. Yeah. Questions? So this is kind of I'm giving you a hint, so that for your next quiz that you get some of these questions. Okay, so reaction coordinates, again, we are getting a little bit to the philosophy of the reactions. So just to know how does it work and what is the meaning of activation energy. Okay, so we call it reaction coordinate. What does it say, the reaction coordinate? If you have A plus B, C, whatever is that. I mean, In this course, we don't go to the chemistry. We just look at it as A, B, C, D. So we make it simple. So if A plus BC gives you A, B plus C, correct? So it's not going to happen like that. So in reality, there are in thermodynamic, what will happen? This is the initial stage and this is the final stage. And that's what is important in thermodynamics. In kinetics is different idea. So we care also about the pathway of the molecules. So that is important for us. And that kind of dictates how fast or slow the reaction is. In thermodynamics, you just care about your initial place. You go from here to Vancouver, here, Calgary, and Vancouver. But in kinetics, we care how route you are going to take it. So that's important. So these coordinates and this activation energy just kind of shows you how the molecules need to go through the hills and valleys to get to the final stage. Like let's assume we are going to just define something like that. Just very approximate. It's not very detailed. So that would be the potential energy. The potential energy. Okay, and that would be the reaction coordinates. That would be the reaction coordinates. What does it mean? It means that we have A plus BC here. So whatever this number is, this is the initial energy of these molecules. And this is the final ones. This is the final one. So that's AB plus C, the final energy content of the product. So if you see the molecules should go over this hill. So they should go over this hill. And then when they go here, this is a very transient, unstable condition. When the molecules get to the top of this hill, so either they're going to get back, a portion of them they might get back, or a portion of them they might go over this hill. So they are not going to stay here for a long time. So, but you have a very unstable transitional stages over here. So we call it this. We call it A, couple of points, B, a couple of points. C means that a transition between A, B, and C. And then when the molecules get to that hill, so they are going to just come down and then to their final status, which is more stable, which is your product. So in reality, you might have more than these hills and valleys. So you might have even a few of them. And then this one kind of shows you your activation energy. So in a sense, activation energy is the difference between the initial value, initial energy of the reactants, minus the final energy of this one. So obviously, if it's here, so you have, if your value is going down, so the value is a positive, so you need a lower energy. Or if this value is high, so you need a higher activation energy to achieve this one. This is kind of showing the energy play between the reactants and the products, and how much energy you need to provide in order to this energy happen. So no matter what, you provide the energy. Even if the final stage of the product is lower than this initial stage, it's not like, oh, we don't need energy. You need energy because the molecule need to go over this hill and then come down. So the final value might be lower than this, right? But that doesn't mean that you don't need energy. So you need the activation energy to activate the molecule. But the final stage might be more than this one, or might be less than this one. So that's kind of the condition. So the activation energy can be thought of as a barrier to the reaction. So I'm going to write it down. So then the activation energy can be thought of as a barrier as a barrier to the reaction. So what it does, this is the activation energy. So what catalyst does, if you use, we are going to just learn about catalyst towards end of the course. So the catalyst will shrink this hill. Okay. So rather than, this is the activation energy now between here and this top of this hill. So rather than this, it's going to go like this. So it lowers the activation energy. So therefore, would be the more possibility of the reaction to take place. Okay, so because just again a couple of definition, I will put it on the board. So why there is an activation energy? The question is, why is there an activation energy? Activation energy. So why we have it? So the molecules, the molecules need energy. Energy to distort or stretch, stretch their bonds, in order to break them. Because there are some bonds, so between A and B, there are some bonds that these needs to be broken, and then the new bond needs to be formed. So you need some energy to break these bonds. Otherwise, it's not going to happen. Break them and thus form new bonds, and thus form new bonds. I'm going to go to the next page, so write it down. So the molecules need energy to distort or stretch their bonds in order to break and thus form new bonds. Okay? And thus form new bonds. And as the reacting molecules, I'm going to go to the next page. So as the reacting molecules come closer together, they must overcome. There are some barriers that the molecules can overcome. They must overcome both steric, we call it steric, so I will mention what is that, and electron repulsion, and electron repulsion forces in order to react. So when you bring the molecules, if you again get back to 201, when you bring the molecules close to each other, there are some forces that you have to overcome. One has to do with the polarity of the molecules, and the other one is because of the steric one, means there are a dust of electrons around the atoms. When you bring those close to each other, that again would be a repulsion that molecules need to overcome. So these are the forces that demands additional energy in order to reaction takes place, and we call this one activation energy. Okay, so again, a little bit of physics of the problem. So just shows how does it work. There is a very mathematical equation that shows the frequency of the velocity of the molecules at any time. So we call it distribution of velocity. So it's a distribution of velocity. So what it is a Maxwell is a famous equation. We call it the Maxwell-Boltzmann. Again, the name of two scientists. Distribution of molecules. Distribution of molecules. So what does it say? It says that f of u, temperature, basically the function of velocity of the molecules, and temperature, which are two important parameters, is a lengthy mathematical equation, is 4 pi m 2 pi kt. This is the constant, Maxwell constant, 3/2 e minus m u squared 2kt u squared. So it's f of u and t, 4 pi m is the mass of the atoms or molecules, 2 pi kt, 3/2 e minus mu squared 2 kt u squared. So if you is very keen to know how does it look like, so if you have f of u t in the f of u and t in the vertical axis, and you have u in this axis, so it's kind of depends on your temperature, gives you some bell shape so this is different t, like T1, T2, T3. So if you look at this one, that shows kind of a bell shape of the distribution of the velocity. What does it say? Look at let's assume this curve. This curve, this is a plot of this one, of this equation at T1. So that shows what is the distribution of the molecules at this temperature. So what percentage of molecules have this velocity, what percentage has this velocity, what percentage has this velocity, shows statistically how the velocity of the atoms or molecules are distributed over a range. Okay, so that's what it does in reality. We don't get to the detail of that one. Again, the intent is just to give you some idea how does this one work. Yes, please.
This velocity is the molecule velocity in general, or?
Is molecules velocity. Let me just show you a quick example. I'm trying to find this. Okay, one of this. Okay, here we go. So let's assume this is a typical graph of this one, f of u and t, like this one. So if you look at it, like this graph, the way it shows, let me see if I have it here. Okay, so this one shows, like for example, you want to find the number of, like you have this T, you want to find the molecules, statistically, how many of your molecules, what percentage, like this is versus EA. So the other one was versus the velocity. That acts similar to that one. So for this one, for example, we are going to find, this is the E, this is the E, this is the F. So similar to what we had for the velocity. I'm just making an example. So that one shows what percentage of molecules have the energy between 5 and 6 in terms of the energy. So what you do, that's a kind of a rectangle over here. So it's 5 minus 6 times 0.083, which percentage-wise means 8.3% of your molecules have the energy between 5 and 6. Assume that you replace this one with the velocity. Shows the same thing. Shows like 10% of your molecules have this, like have this velocity, like whatever, 10 meters per second, or is much more than that. It's kind of statistically shows how molecules have different velocity, because not all of them have the same velocity. Okay, so I don't get more detail. As I said, this is more physics of the problem. I will get back to more reaction parts. So the only remaining, which I was hoping I finished this one, is a reversible reaction. And then that concludes chapter 3. So you have most of the material of chapter 3 if you want to review. And so it's a reversible reaction, means A gives B, B gives C, how the rate applies to that condition.